Hey guys, today I'm going to do a video on the properties of gases. So, molecular motion in a gas is totally random, and the forces of attraction are so small between them, gas particles, that they're able to move freely and independently of each other. They're simpler and easier to understand than liquids and solids. And all gases have the following characteristics. They have much lower densities than liquids and solids. They are the most compressible state of matter, and they assume the shape and volume of a container in which they are stored, and they mix evenly and completely when stored in the same container. So if you have two different gases, you mix them in a container, they'll mix evenly and completely. So some substances exist as a gas as standard states, and some don't. Most substances can exist in multiple states: liquid, solid, or gas, or plasma. Temperature and pressure determine which state a particular substance is in at any given time. And to be meaningful in our comparison of different substances in different states, we must set some conditions. And these conditions are SATP, which is standard ambient temperature and pressure, which is 1 atmosphere and 25 degrees C, or 273.15 Kelvin. So let's look at pure elements, ionic compounds, and molecules, and compare how they can be gases at certain temperatures. So pure elements, some elements exist as a gas at standard state, are standard ambient temperature and pressure, and these are H2, N2, O2, and ozone, O3, Cl2, F2, and all the noble gases. So that's pretty much, or is, all the elements that exist as a gas at these conditions. Ionic compounds, these do not exist as gases at SATP. These compounds are held together by strong electrostatic forces, and they need a lot of energy to pull them apart and convert them to a gas. So molecules, some exist as a gas at SATP. So examples of this are carbon dioxide, carbon monoxide, and ammonia. But most are liquids and solids at room temperature and at 1 atmosphere. Much easier to convert a molecule to a gas than it is to convert an ionic compound, and that has all to do with intermolecular forces. Okay, so a big part of gases is pressure. So pressure of gases, because gas particles are always in motion, they collide and exert a force on the surface they contact. So when in a balloon, that's what's keeping the balloon blown up. So pressure is defined as an applied force on a unit area. The SI unit for pressure is the Pascal. So pressure is force over area. The SI unit for force is a Newton, and the SI unit for area is meter squared. And so a Newton over a meter squared is Pascal. But because a Pascal represents such a small amount of pressure, other units are commonly used to express pressure. So if we have 101.325 pascals, that's equal to 1 atmosphere, which is what pretty much we feel right now in this room. And then that's equal to 760 millimeters of mercury. So that is, millimeters of mercury is something, a unit derived from a barometer, which you can look up. All these units express the same physical quantity, therefore they can be used in conversion factors. And they express the standard atmospheric pressure, or the pressure that air exerts on any surface exposed to the Earth's atmosphere at sea level at 0 degrees Celsius. This force is equal to the weight of the column of air that an exposed surface is under. So you might be thinking, okay, so if I'm standing on the surface of the Earth, there's a column of air above me, it's squishing me, it's giving a pressure on me, but what happens if I stand under a roof, like here? Is there any pressure on me? Well, yes, because air, like water, is a fluid, and in fluids the pressure is all around you, because just think of the collisions between the particles and other well, not really other particles, other particles, and they come around and they're all around you and they press on you from all different directions. So that's why when you hold up a piece of paper in the air, it doesn't bend from the pressure of the atmosphere, because there's just the amount of particles pressing up from the bottom of it, making a flat piece of paper. So the next video we're going to do some gas laws, talk about some ideal gases, and we'll probably derive the ideal gas law.